My name is Daniel, and I'm presenting our work on unified compilation for lossless compression and sparse computing. Real-world data across many domains contains a significant amount of redundancy, which can be used to both speed up computations and compress it for more efficient storage and transmission. For example, if we consider a database of reviews from an e-commerce site, it can naturally be represented as a tensor, with dimensions for the user, product, and keywords within their reviews. Users review only a small subset of all possible products, so this tensor will naturally be very sparse or have many zero entries. And storing this tensor with all of those zero elements would result in a dense representation using over 100 exabytes, where aligning the zero values and storing it using a sparse representation results in using just 13 gigabytes. Sparsity, however, is a narrow form of compression, which is focused on eliminating zeros. If we consider data from other domains, such as video and image processing, there may not be significant sparsity to take advantage of. In these sketch images, for example, only the pure black pixels are stored as zeros, so there's little benefit in using sparsity. However, while there may not be significant sparsity, there is still significant redundancy. This clip and images have many repeated values represented, and this type of redundancy is often taken advantage of by compressing the data, as storing videos or images uncompressed can be extremely infeasible. If we look at binary medical images such as these, there's significant redundancy in both the black and white regions. And using sparsity limits us to only the black regions. So using compression enables these to be stored much more compactly. In addition, in a domain such as medical imaging, it is often necessary to ensure compression does not alter the data, so lossless compression must be used. We can see that sparsity and lossless compression are two different approaches for handling repetition that occurs within data. And they traditionally have had different applications, with sparse formats used to accelerate computation and lossless compression formats used for efficient storage and transmission. For example, different sparse formats can be used for thermal simulations, sparse neural networks, data analytics, and mesh simulations, and many more. We're looking at the lossless compression side of this slide. This first set of formats are core techniques, usually used as part of a more complex compression algorithm. This next set are for general purpose compression. But to get the most efficient use of storage, domain-specific information can be encoded into these formats. For example, here we have formats designed specifically for audio, image, and video. So if we consider this abstract view of speed up versus compression ratio, where higher is better for both axes, we see their different goals. Sparsity has traditionally focused on speeding up computations with more modest compression, where lossless compression is more focused on reducing storage costs. And this is potentially at the expense of slowdowns, even over dense computation. Previous work has enabled computing directly on compressed data, which can provide speedups when performing computations. However, typically, in order to compute with a lossless compressed format, decompression is first required, followed by computing on a dense representation, and lastly, recompressing the result. If we look at this concrete kernel, edge detection and medical images, we see this pattern occur. Sparse computing yields higher performance with a more modest compression ratio, while computing using a lossless compression format results in much higher compression at the expense of slightly worse performance than dense. And we'll show through the rest of our talk that by unifying both of these approaches, we're able to generate code which computes on compressed data, allowing us to get both the highest compression and compute performance. We built our techniques using Taco, a compiler for sparse tensor algebra. So let's first look at how sparse tensors can be stored. We can elide the zeros from this matrix, but then additional metadata is needed to determine the row and column coordinates of any given value. The simplest approach is to store the coordinates of each non-zero element. This allows efficient lookup of any given value's coordinate in the matrix. However, there's duplication when storing the row's coordinates. So by using the compressed sparse row formats, otherwise known as CSR, which is one of the most popular formats for storing sparse matrices, we store each row in a contiguous segment of the calls array, which allows us to reduce duplication of the row's coordinates. To see how Taco abstractly represents different tensor formats, let's look at an example of a three-dimensional sparse tensor, which is stored in the format on the right. Conceptually, this format stores each slice of the matrix of the tensor as a matrix in the coordinate format. But what's important to note here is that all these arrays can actually be grouped into data structures, each of which encodes only a single dimension of the tensor. The first array encodes the coordinates of each slice of the tensor as an implicit range from 0 to 3 exclusive. The next two arrays then store the row coordinate of each non-zero element in the tensor, also keeping track of which rows belong to which slice of the tensor. Finally, the last array here stores the column coordinates of every non-zero element in the tensor. This alternate view of this tensor format allows us to view it as a composition of what Taco refers to as level formats, namely dense, compressed, and singleton, each of which encodes only a single dimension of the tensor. And using these level formats, we can actually represent the sparse matrix formats we've looked at so far. By using the dense level format to store the row dimension, and the compressed level format to store the column dimension, the matrix format we obtain is the same as CSR. If instead we use the compressed level format to store the row dimension and the singleton level format to store the column dimension, then we get the coordinate format representation of the same matrix. So by composing these level formats together in different ways, it's possible to create not just the two sparse matrix formats we've looked at so far, but also a larger number of tensor formats, including the coordinate format for tensors, and various block matrix formats, and many more not shown on this slide. So far, we have introduced Taco and its techniques for representing sparse tensors. Next, I will motivate and introduce our new abstractions for representing lossless compression formats within the framework of sparsity, and introduce the two new level formats we have added to Taco. I will then discuss the new optimizations and code generation techniques we added within the compiler, enabling us to generate efficient imperative code using our new formats and the abstractions they're based on. If we consider this matrix, it has many zero values, so it may be natural to store it using the CSR format. However, a closer examination of the matrix reveals that there are more one values than zeros. By allowing the value the matrix elides in its sparse representation, called the fill value, to be 1 instead of 0, we can get a slightly more compressed representation of this matrix. Though even with this added flexibility of changing the value the matrix is sparse with respect to, we still have to store the 0 values we initially elided. And looking at the patterns present in this matrix, there are a number of repeated values besides 1s and 0s. We could get better compression if we could represent all of these repeated values succinctly, not just choosing one of them. And the lossless compression format, run length encoding, otherwise known as RLE, would be most efficient in this case, as it stores each value only once with the number of times it repeats. So by using a different fill value for each of these regions in the matrix, we would be able to represent run length encoding within the framework of sparsity. So let's focus on the first row of this matrix to see how we can do this. There is now not a single fill value we can use for the entire matrix, or even just this single row, but by allowing the fill value to be a dynamic property, it could be updated for each value, encoding the runs using the fill value. So we can store each of these values once, along with their coordinates, and then use them as the fill value. So let's see how this new format represents this row of the matrix. As the first value is at coordinate 0, we use this value, 1, and then also use it as the fill value. The next coordinate stored is 3. So the values at coordinates 1 and 2 are represented using the fill value. So we just updated the fill value to 1, so we use that value for the next 2 coordinates. By storing the coordinates along with each of the values, we implicitly store the run lengths. And this allows us to represent this first run of 1s. Now, moving to the next defined value, it's also used in the row of the matrix, as well as being used for the fill value. And as the next coordinate explicitly stored in this representation is 6, we use the fill value for the next 2 coordinates at 4 and at 5. Finally, the last value of 5 is used, and the fill value is used for coordinate 7 of this row. Thus, by changing the fill value to each defined value, we can represent run length encoding within the framework of sparsity. So we added this new run length encoding level format into Taco. And if we compare it to the existing compressed level format, we can see the representation advantages of having multiple fill values. In the compressed level format, we're only able to choose a single fill value. So there's limited compression available for this matrix, whereby allowing it to change dynamically over each of these regions, we can represent this matrix much more compactly. In addition to our run length encoding level format, which we've just introduced, we also added an LZ77 style level format, which can represent more complex forms of redundancy, such as this pattern of 3 values repeating. LZ77 uses a sliding window into previous values to represent repetition. Our format uses these 2 numbers, the distance into previous data, and then the number of values to repeat. But for more details on this level format, I encourage you to see our paper. So now we've introduced the new abstractions we integrated into Taco to enable representation of lossless compression as a form of generalized sparsity. We also introduced the 2 new level formats, run length encoding and LZ77. Next, I turn to the new optimizations and code generation techniques we use to generate efficient code using these abstractions. Taco has 2 main forms of computation, element-wise and reduction operations. And we will first consider element-wise computation using this example of multiplying 2 run length encoded vectors. While computing at each coordinate would result in 8 total computations, we can see that there's only 4 unique computations being done in this case. So I will show how the compiler is able to generate code which aligns this redundant computation and directly outputs into a compressed format. The run length encoded format we added into Taco stores each repeated value once along with the coordinate it first appears at. And the compiler uses this representation to co-iterate these inputs. Whenever the generated code encounters a defined value, it performs the necessary computation which in this case is multiplying the values 1 and 6 to produce the output 6. However, these next two values are both fill values. So the compiler should be able to generate code that recognizes this redundant computation. When it's generating code, the compiler queries the output level format, in this case, run length encoding, to determine how it can insert repeated values into the output. The run length encoded level format implements this as a no-op, as it implicitly stores repetition. So by writing the value 6 at coordinate 0, this implicitly represents that the value 6 is repeated until the next coordinate. So this allows the compiler to generate code which skips iterating and computing with the next two fill values. So to iterate, the generated code moves the position of each input vector to their next defined value. It then can use the smallest coordinate to determine and perform the next computation which is required. It then continues iterating following this same strategy. And when there is not a defined value, the fill value at that particular point in iteration is used. So we can see how the compiler is able to generate code which performs only the necessary computations while also producing a compressed output. This optimization is possible by using the definitions present within the level format. So while we presented an example using run length encoding for both of these inputs and outputs, this optimization is applicable more broadly, including ones not yet implemented. Next, we consider reduction operations. Using this example of performing a dot product between a run length encoded vector and a dense one. We can note that there's only 3 unique values stored in this run length encoded vector, even though it's representing 8. So using the distributive property, we can factor out the repeated multiplication by these elements. And this reduces the total cost of computation while still producing the desired result. So we implemented our techniques as an extension to Taco, both integrating support for our new abstractions into the format language and adding compiler support for generating efficient code using these new abstractions. And we added our 2 new level formats, run length encoding and LZ77. Next, I turn to our evaluation of our technique. The first kernel we investigated was alpha blending, which takes images such as these and produces a blended output. If we compare the compression ratio between dense, sparse, and run length encoding, we see that while sparsity enables us to get significant compression by treating the white pixels in these images as the fill value, our run length encoding format, due to its ability to handle both the white and black pixels, has significantly higher compression. And we see a similar story when we compare the performance of computing directly on the sparse representations and computing on our run length encoded format. We also compare to the popular open source image and video processing library, OpenCV. While OpenCV has higher performance than the dense codes generated by Taco due to its hand optimizations and vectorizations, computing directly on compressed representation still yields the highest speed up over dense. The next kernel we investigated was edge detection on medical images using this kernel. As with the previous evaluation, we see that while sparsity has a modest compression ratio, using our run length encoded format, we get a much higher compression. And if we compare the performance, we see that our run length encoded format yields the highest performance as well. The final kernel we investigated is compositing a subtitle onto a video frame using a mask. And while computing directly on our run length encoded format produces faster code than the dense code generated by Taco in most of these cases, we see that OpenCV outperforms the generated code on run length encoded most of these video clips. However, as this data, it needs to be stored compressed, in order to make this a fair comparison, we need to include the time it takes to decompress the data, do the computations either with Taco or with OpenCV, and then recompress the results. And adding these costs, we see that in all 12 of these video clips, computing directly on the run length encoded data yields the fastest result. In conclusion, we can automatically generate kernels that compute with both lossless compressed and sparse formats. And our new abstractions enable implementation of many lossless compression formats, of which we've implemented 2, showing that by unifying sparsity and lossless compression, it's possible to get both the best compression and the best performance. Thank you.